Now we want to find the area between two curves. The fundamental theorem of calculus tells us how to find the area between a curve and the x-axis. And the formula for the area between two curves is based on the fundamental theorem. So let's draw a picture, and we'll write down the formula. So suppose we have these two curves, and I'm assuming they don't intersect between A and B. I'm assuming that F is on top and G is on the bottom. And this is the area that we want to find. Okay, I'll call it A. So the area is equal to the integral from A to B of the upper function minus the lower function. And we can easily see that this is based on the fundamental theorem. The fundamental theorem says the area from A to B of F, the integral from A to B of F is the area between the upper curve and the x-axis. And then if we just subtract off this lower area, we get the area between the curves. So that's what we're doing here. We're subtracting off the area from G of x between A and B, this lower area, to get the area in between. So let's apply this formula in example 1. So here are our curves. This one is the upper one, F, and this one is the lower one. Okay, now if we have a little bit of knowledge of the graph, we can easily see that. This is, even without the graph, this can be done if we just determine that this curve is on top and this curve is on bottom by just substituting in, if we assume the curves don't intersect. And we can just substitute in a value in between 0 and 2, like substitute in 1, for example. If we substitute in 1, here we get 5, and here we get 1, so we can see this one's on top. That is assuming the curves don't intersect in the middle, and we can see that they don't by actually finding the intersection points. In any case, to start with though, let me draw the graph since this is an easy one to graph. Minus x squared plus 6 is the curve minus x squared lifted up 6 units, so it looks something like this. Here's the point 0, 6, and this is y equal minus x squared plus 6. And y equal x is a straight line, slope 1. So this is y equal x. So if you have a little bit of knowledge of the graph, you can see that we have two intersection points, which we'll find in a minute. All right, so let's find these intersection points. And that we do algebraically by setting f equal to g. So let's do that. So now we're going to find intersection points. All right, we'll set minus x squared plus 6 equal to x. Let's bring everything over to the right-hand side. So we have 0 is equal to x squared plus x minus 6. This is a quadratic. To solve it, we'll try factoring. And this does factor. Okay, x plus 3, x minus 2. So we have two intersection points, x equal minus 3 and x equal 2. So this is the, right here we have the minus 3. And here's 2 somewhere over here. That's 2. Okay, so we see that this point, we want to find the area from x equals 0 to x equals 2. Well, here's 2 right here. This 2 is the x value of the intersection point. So this is the area that we are looking for. That's the area we want to find. From 0 to 2, this is the upper, this is the lower. All right, so let's use our formula, and we have that the area is equal to the integral from 0 to 2 of the upper minus x squared plus 6 minus the lower. Okay, let's just write that out. We don't need those parentheses. Minus x squared minus x plus 6 dx. And we'll integrate, power rule, minus x cubed over 3 minus x squared over 2 plus 6x. And substitute in our limits of integration. Okay, here we get minus 8 over 3 minus 4 over 2 plus 6 times 2, that's 12. All right, that's minus 8 thirds minus 2 plus 12. Let's change everything to thirds. Minus 8 over 3 minus 6 over 3 plus 36 over 3. That's equal to 22 over 3. So that's our area. Let's suppose we had no knowledge of the graph. Well, we could just find the intersection points, start here like we did, and we see that we have 2 intersection points. We would still integrate from 0 to 2, to this 2, because actually that's what the instructions said all along, to integrate from 0 to 2. And we would, in order to determine which is on top and which is on bottom, we could just substitute in a value. Like substitute in 1, like we said before, between 0 and 2, we could substitute in 1, and we see that this, if we substitute in 1, we get a 5 here, we get a 1 here, so this one's on top. Okay, so we could actually do this without any knowledge of the graph. Now we want to find the area between these two curves. So let's start by finding the intersection points. Set the two curves equal to one another. All right, let's get 0 on the right-hand side. And this is a quadratic, so we'll try factoring. And it does factor. That's x minus 3x plus 1. Okay, wait, let me just rewrite that. All right, and now solve. So we have x equals 3, x is equal to minus 1. So those are our 2 intersection points. Let's look at the graph, although it's not necessary to draw the graph in order to do this example. All right, so here's a rough picture of the graph. Y equals minus x squared plus 3. It looks like an upside down parabola, and the vertex is up here at 0, 3. And here's y equals minus 2x, a line with slope negative 2. All right, and we see that the intersection points are at x equals 3 and x equals minus 1. So here's minus 1 right here, this intersection point. Okay, and here's this intersection point right here. This is 3. And we want to find this area. So we see that the upper curve is minus x squared plus 3, although we could just substitute in a value like 0 to figure that out into both curves, and we would see that this one is above this one. All right, let's apply our formula. The area, the shaded area, is the integral from minus 1 to 3. And we have the upper curve minus x squared plus 3, and we're subtracting the lower curve. All right, so let's just simplify the integrand over here. We have minus x squared plus 2x plus 3. All right, okay, so now let's apply the power rule, and we have minus x cubed over 3 plus 2x squared over 2, that's x squared, plus 3x, and we're integrating between minus 1 and 3. Okay, let's substitute in 3, and we have minus 8 over 3 plus sorry, minus 27 over 3. This is a 27. That is 3 cubed, minus 27 over 3 plus 3 squared plus 9, and plus 9, 3 times 3. Okay, now we're subtracting, now we're substituting in minus 1. So here we have minus minus 1, that's 1/3, plus 1, minus 3. Okay, and if we work this out, this comes out to 32 over 3. Okay, we want the area between y equal x to the 4th and y equal x. Let's find the intersection points. We'll set x to the 4th equal to x, or x to the 4th minus x equals 0. Let's factor this. First factor out an x. Here we have a difference of 2 cubes, and we have a formula for factoring a difference of 2 cubes. Let me just remind you, a cubed minus b cubed is equal to a minus b. A squared plus ab plus b squared. All right, so we're going to use that to factor x cubed minus 1. So we have x times x minus 1. And here we have x squared plus x plus 1. So we get x equals 0 as an intersection point, x equal 1. And here, this one has no real solutions, and you could see that by calculating b squared minus 4ac, the discriminant, which is 1 minus 4 times 1 times 1, it's minus 3, it's negative. So no real solution. So we have these two intersection points. All right, these are easy to graph. Y equal x to the 4th. It sort of looks like y equal x squared, but it's a little flatter at the bottom. And the line y equal x. So this is what the curve looks like. Here's y equal x, and here's y equal x to the 4th. And here are the two intersection points, 0 and 1. This is 1, 1, 1 over here. 0, 0. So this is the area that we're looking for. So we're going to integrate between 0 and 1. X is on top. All right, so that's equal to x squared over 2 minus x to the 5th over 5, and we're substituting in. So we get 1/2 minus 1/5. Okay, and the other limit is 0, so let's just change everything over to tenths. So that's 5/10 minus 2/10, and that is 3/10 for the area.